Welcome to the Private AI Lab, the podcast where we experiment, explore, and debate the future of AI behind the firewall. I'm your host, Johan, and every month I have a guest in the lab to break down real-world use cases, challenges, and innovations shaping private AI. In this episode, Adam Grzywaczewski from NVIDIA joins me to talk about the subtle art of inference. What is it? How do you scale for inference? And what is the impact that models have when it comes to sizing, accuracy, and latency? Enjoy the episode. So, Adam, welcome to the show. It's a huge honor to have you here. This is the actual 6th episode, and along the way, I gathered a ton of questions around all of the different topics we recorded before, like on private AI, on local hardware, on inference, on the different types of GPUs, and I have the feeling that I can finally have the opportunity to ask the questions at the source. And, you being part of NVIDIA, again, great honor to have you here. But before we dive into every detail of the topic of today, could you please introduce yourself and explain what it is that you do at NVIDIA?
Sure. So my name is Adam, and I've been at NVIDIA for 9 years now, I think. And at this point in time, I lead an EMEA organization that is responsible for key technical collaboration with our key partners and customers. So we're, in effect, an interface between our research, product teams, and engineering teams. And our responsibility is to work with a very small subset of our key customers to make sure that, one, we understand how people are using our technologies, both hardware and software. We're given an opportunity to shape it, so to help our product and engineering teams decide what is it that we should and should not be building, and also help unblock our key customers to make sure that they are successful. In a sense, that's the essence of NVIDIA's business model. We are successful via success of our partners and customers. So if we can accelerate that, that also accelerates our scale out and success.
Now, for me as a fellow technologist, that completely makes sense. But how would you explain something like that at a dinner party? How would you explain to, a family member what it is that you do?
Sure.
What is the value that you bring?
So if you watched Pulp Fiction, I think my team is like Mr. Wolf. Yes, we're here to solve problems. In life, almost nothing ever just works first time around, especially when you have absolutely new technology. So think about the time when we've introduced 16-bit numerical formats, mixed precision training. It didn't just work. It just works today, so we don't have a role to play. But at that point in time, no one knew how to force it to work. You had to do a lot of manual interventions to actually force it to work, like choose individual layers that you want quantize and make different scaling interventions depending on a neural network of choice. Not only the documentation didn't exist, but the outline, the idea of the documentation didn't exist because it was not obvious how to make what interventions when. We step in at that border. So we step in at the point where an idea was proven for the first time by our either research or engineering teams, but it's not necessarily obvious that it works most of the time. Yes. And we are the group that makes sure that the technology that we create works most of the time, yes, which is completely not obvious for new technologies. So we can fix problems, and whenever you use something for the first time, there are a lot of problems.
Well, first of all, I sincerely love the analogy around Pulp Fiction and Mr. Wolf in particular. But second, in the fact that you've been with NVIDIA for 9 years, but also that you've been at the forefront of experimenting, if you will, it'll probably meant that you saw a lot of different AI challenges that you solved. So what was your first AI challenge that you actually solved? And can you kind of elaborate a little bit about the project or the experiment?
Sure.
And did it go as planned or not?
So one of the most important things that I've ever done, from my perspective, my selfish perspective, that it was something that I didn't do at NVIDIA. I was working at Jaguar Land Rover at the time in the research department, and we've just concluded a wave of projects, and we're sitting down with the team to try to ask a question of what to do next. Yes, and at that particular point in time, Andrew Ng just left, I think, Google and joined Baidu, and was working an amazing work around automatic speech recognition. So my team, as naive as it was at the time, we decided to try to reproduce that. And that was, of course, fairly quickly an impossibility at that point in time. They were already scaling out the training process to very large systems, which we did not have, but that failure helped me understand the fact that neural networks will work. Yes, I think it became very obvious to me at that point in time that with enough cycles, neural networks have an opportunity to work well, not just in automatic speech recognition, but like in every conceivable application space of artificial intelligence, and at that point in time, I've decided to do something about it and try to move to a company that focuses more on that technology stack. So I did what everyone would do. I've applied to Baidu, and I even went for an interview to the United States. At that point in time, they didn't. I didn't fit the bill, I think, for the research scientist. But I was offered, if I remember correctly, a role of a product manager, which we were just about to decline. But because of the preparation that I've done to apply for that role, i.e., cleaning up, CVs, LinkedIn profiles, publishing online, just someone from NVIDIA reached out. So from my perspective, that was a very important learning and a failure, without which I don't think I would be here today.
Awesome. Well, then this is a great segue and bridge into experiment number 2, the deep dive. And in this episode, we're going to talk about a couple of topics, and let's start with the state of AI inference. Because with someone with so much experience in the field, but also someone who sees a lot at what different partners and customers are doing, I'm guessing you have a good understanding of of the state of AI inference. And let's start with the first question. So, what are the biggest bottlenecks teams hit when moving from training to inference?
Sure. So inference has changed in the last couple of years. So there was a very long period of time where inference was a completely different problem than it is today. So first and foremost, for a very long period of time, it was embarrassingly parallel, meaning that you could have an isolated instance of a model, and you could send a request to that model, and you'd just get a response. And models were relatively small, so not only you could fit one in a single GPU, but very frequently, historically, you could fit a lot of different instances of the model in a single GPU. So we were working on completely set of problems, completely different set of technologies. So if you maybe remember technologies such as Triton Inference Server, one of its key capabilities was its ability to execute multi-instance GPU setups, whereby a single GPU could have several copies of the same neural network or multiple copies of different neural networks. It had concurrent model execution, and that would allow you to do that even without the hardware boundaries offered by the make technology. That has now changed. Yes, the models that we are working with are autoregressive, meaning that their execution pattern is much more complicated. It's divided into two completely different steps. Models grew quite considerably. So very frequently it became obvious that you cannot just host them on a single GPU, single server, but that many of the larger architectures now need to spawn across multiple servers. Additionally, now the explosion of a mixture of expert neural network architectures further complicates the deployment, in a sense that suddenly it's not enough to just have 1-2 servers per instance of a model. Modern cost-effective deployments of mixture of expert architecture spawn across a much wider estates of GPUs to be most cost-effective. And also communication patterns within those inference systems change dramatically, because the structure of mixture of expert communication is not as predictable as it used to be. And neural networks are no longer equally balanced, i.e. the entire neural network is by definition not participating in the execution of the forward pass, just a subset of it. So suddenly you have this new family of load balancing problems. Inference is changing, and it will continue to change. And I think that is the biggest challenge for everyone that is trying to thrive in this field. And at the same time, also the biggest opportunity. We're nowhere near done. We have still much more work to do, especially that neural networks that we are using are evolving very quickly, both from the architecture, but also from the inference perspective.
So, and you touch upon a really interesting point there, which is it's less predictable, right? But at the other hand,
the execution pattern is, yes.
Yeah, but on the other hand, we try to help customers to to build and scale their platforms and their infrastructure in a way that makes sense to the business. So how does NVIDIA help customers to scale their models efficiently, especially across industries like automotive or NLP?
Well, so long time ago we've realized that it's just not enough to design silicon. Yes. You can pick up a GPU from a truck or from a shop and shout at it as much as you want. It will not do anything interesting. You do need the end-to-end software to be able to take advantage of those technologies, and we treat that very seriously. That is why we always were proud of our strategy to address the problem via the end-to-end platform. So we are trying to develop all of the tools that the community needs for inference as well as training. But since today's talk is focused on inference, let's focus on that. So we're developing software utilities across the entire stack. At the very, very bottom of the stack, of course, you have CUDA. But now we also have completely new communication libraries. So many of the listeners might have heard about our Nickel library, NVIDIA cumulative communication library that is extensively used for GPU to GPU communication during the training process. Now we also have a dedicated library focused on communication for inferencing workloads called Nixel. So that's somewhere kind of at the bottom of the stack, if you wish. In parallel to that, we have a new, relatively new library that is a derivative of TensorRT called TensorRT-LLM that is designed to support acceleration of autoregressive neural networks. As part of that, we have utilities such as model optimizer that are designed to help with distillation, quantization, and pruning of neural networks. And on top of that, we have libraries such as Dynamo that bring not just naive inference capabilities, but are bringing some of the more advanced features like very large-scale disaggregated execution. Yes. And on top of that, we also have names that are targeting, the users that maybe don't want to be exposed to this level of detail, but receive inference capability that is a very good throughput latency out of the box. So we try to develop software across that stack. And we don't stop there. We are acutely aware that we cannot succeed alone. That is why we're investing a lot of engineering effort at helping also our partners and open source ecosystem to integrate that tool. So we're working with all of the suspects, including SGLang, VLLM, to make sure that they use as much of our pre-built optimized components as possible, and that we also help them optimize their stack on our GPUs.
Yeah, and we're not going to dive into that during this episode, but I think the recent acquisition or the recent announcement of the acquisition of SCAD-MD is a perfect example of that as well, right? So
But that's
again,
more
it's
in the training stage, yes.
yeah, and
LLM is a very important utility for countless groups across the globe that are training neural networks.
yeah. So coming back to still to the topic of inference, and you mentioned Dynamo. You also mentioned TensorRT and Tensor Inference Server before. So how do these tools and Dynamo being the successor to Triton, if I'm not mistaken, how do they fit into the bigger picture?
So TensorRT as a utility is quite old. It existed at the point in time when I joined NVIDIA. So I don't know how old it is, but it will be close to a decade old, a bit more, a bit less. I would have to check. But it was really designed for different neural networks in a sense that it wasn't natively designed for autoregressive execution. Autoregressive just means that modern large language models don't generate the response to your question in a single forward pass. It means that they generate it one token at a time. So when you ask a question, you get one token of an answer and you pass it back in. You get a second token of an answer, you pass it back in, and you get a third token of an answer. So you really don't want to execute it naively just with PyTorch or TensorRT without taking into account that autoaggressive execution, because that loop is extremely repetitive and there is a bunch of tricks that you can implement to do a better job. And so we've created initially a library called Faster Transformer, and now that evolved into what is now TensorRT-LLM that allows people to deal with complexities of autoregressive model execution. So it provides, yes, the basic capabilities to accelerate, I don't know, KV cache execution, but also it has a lot of very advanced features around speculative decoding. It's a state of the art, admittedly, with a relatively steep learning curve library for those that truly care about the cost of their inference. Yes, but it's a low-level library. It doesn't provide a server, it doesn't provide a service. So Dynamo brings some of those large-scale operational capabilities to TRT-LLM, but also to other execution backends. So again, we're trying to follow the same philosophy that we had with Triton Inference Server, whereby we wanted to create the best tool for everyone, regardless what execution engine they use. So you can use Dynamo with TRT LLM execution backend, but you can also use it with VLLM, and it provides some of those more execution pattern focused features, such as KV cache hour routing, such as disaggregated execution, and overall a set of utilities for large-scale deployment and operation. So those are not things that you can ignore when you have large volumes of traffic. Like without some of those quote-unquote tricks, your inference performance will be way off from what it could be. So you'll be kind of spending dramatically more than you should. So those are technologies that are worth checking out.
Yeah, you mentioned a couple of software-based technologies, and Jensen Huang, your CEO, he called by heart Dynamo during, I think, GTC in 2025. Basically the operating system of the AI factory, but an operating system without hardware is also kind of challenging. So when it comes to hardware, what role does hardware choices play in the inference equation today?
Sure. So quite significant. So you have to do all of those things all at once. You cannot just optimize one part of the stack. Hence that is why Jensen very frequently refers to the NVIDIA platform. It doesn't matter how great of a GPU you have if the software to use it doesn't exist, and vice versa. You have to create optimizations across the entire stack. So GPUs, they from one generation to another, they vary tremendously in many different ways. It's not just a matter of, having a slightly faster logic that you had in the previous generation of GPUs. They tend to differ quite significantly when it comes to memory technology. Newer generations of GPUs have significantly faster memory systems, which is something that is very important, especially for the second phase of execution, for the decode phase of the execution of neural networks. But they also differ when it comes to their overall computation capability. So in particular, the new GPUs bring new numerical formats, smaller numerical formats that help tremendously with, again, memory bandwidth. So, for example, Blackwell generation brings new 4-bit precision microscaled numerical formats that are a game changer for anyone that cares about throughput and latency.
I got a DGX Spark on my desk, which when it comes to Int4 does 1,000 tops.
Sure. Yes. But it's not only about Int4. Int4 is actually surprisingly difficult sometimes to use. The Blackwell family brings a 4-bit floating point, microscaled numerical representations. Microscaled refers to the fact that with 4-bit precision, you don't have enough numerical accuracy to represent anything really. So if you think about kind of the window of numbers that you can represent, those microscaled formats allow you to move that window across the numerical axis. And microscaled formats allow you to do it with windows of 16 numbers. Yes? So for every 16 numbers, you'd have kind of this scaling factor that allows you to choose where are you going to be great at representing numbers. And that allows you for stability of both inference as well as training. So there are quite significant innovations that are baked into those systems, and kind of you need to use them if you want to take advantage of the GPUs. To the maximum, not to mention innovations around networking, additional hardware acceleration for miscellaneous operations that are not necessarily computationally bound, but are dominating when it comes to overheads. There are very significant differences between generations of GPUs. We try to continue to push the boundary of what is possible.
Yeah, and one thing that continuously to amaze me is the fact that you guys present a roadmap ahead of, like, a couple of years ahead. We already, and it's, I think that was, to me, one of the biggest surprises of GTC in San Jose in 25, that we already got an insight in what your plans look like for the coming couple of years around like things like memory bandwidth and certain features of the architecture that add value to what you would be doing in a couple of years from now. And I think that's completely different from other companies in the world. It was surprisingly enough for me. It was very surprising to me.
Yeah, so we're in a fortunate situation whereby we have so much work to do. It's actually quite easy to. Of course, things can still surprise us, and neural networks can change. But NVIDIA is very good at adapting. So if suddenly neural networks completely change, we will definitely adapt. But right now, it's quite clear what we need to be doing. Like we know where the work is ahead of us. So Jensen shares as much as we know with the world.
Yeah, and we'll continue to do that. So yeah, definitely looking forward to future conferences. And San Jose or GTC San Jose is coming up very soon. So definitely, I'll link share a link in the show notes around GTC and how people can register. Now, I want to dive into a next topic, which is efficiency, and specifically efficiency techniques. So you mentioned mixture of experts model. You also mentioned models getting bigger, and quantization could be a technology to kind of compress models. But can you explain model quantization and pruning, which you mentioned before as well, in simple terms, and what they actually make sense when it comes to using them?
So I'll try to keep it simple, but in effect, there is a very good reason why those neural networks need to be as large as they are during the training process. Yes, in effect, that makes the optimization process easier. So there is no I'm not sure whether there is anyone that knows a way around making those neural networks big. The thing is that once they are trained, they don't have to be as big as they are. Like the size of those models was necessary during the training process, but most of the neural network after you've concluded training can be removed. So effectively, with that in mind, suddenly you have a bag of tricks that you can use through which you can reduce the size of the neural network. And all of the things that you've mentioned, they take from that bag. Yes. So the bigger the model gets, the bigger is your opportunity to shrink that model. And you have a lot of different techniques that you can use to shrink the model. So if you've trained a model with higher numerical representation, 16-bit or 8-bit, like with Hopper generation GPUs, it is in most cases possible to convert a big part of that neural network, not the entirety, but big part of the neural network to 4-bit numerical representation. And by doing so, you strip down half of the parts of the neural network that you've converted. Yes. It's also possible to prune the neural network and remove elements of it that are not contributing to the output. Yes. But it's also possible to very aggressively distill neural networks. And that's something that myself and my team is focusing on right now. So it is possible to relatively cost effectively take a larger neural network and force its knowledge into a smaller neural network architecture. So one of the most exciting recent development that we've saw in this space from NVIDIA is this architecture called, this methodology called Puzzletron, whereby we take a neural network and we distill it not in its entirety, but one layer at a time. And we don't distill it into just a smaller neural network, but every layer we distill to, say, 20 different candidate layers, 20 different puzzles. And we bring them back together into the neural network that looks like a monstrosity because every neural layer is different. Yes, some of them are gone completely because it turns out that without them, the neural network still operates. But that methodology is actually quite effective in a sense that you can distill models much more aggressively than you could before. So I think the bigger the neural networks will become, the more space we'll have for some of those very aggressive interventions. And this is by all means nothing new. So I would encourage your audience to refer back to quite an old, I think 5-year-old now, Berkeley AI Research Center, BER Lab, they published a paper. I'm not sure whether I will recall the title in its entirety, but I think it was called Train Big then Compress. Yes, in a sense, they lay an argument that is the correct way of thinking about the problem, rather than trying to train a small neural network. It's typically much more computationally efficient to train a much larger neural network and then very aggressively reduce its size. And we are developing a range of tools to help with that. Most of them are finding their way into a library that we call Model Optimizer. But there are also other similar libraries. There's a similar library within VLLM that we're trying to support as much as we can as well.
So are the Nemotron models that NVIDIA released an example of models that went through such a process as well?
Some of them are. So so we are experimenting across quite a lot of dimensions. So first and foremost, most of the models that we are releasing, we would release with some form of quantized variant as well. Yes. We have an entire family of models that were released during the previous GTC called Llama Nemotron that are a perfect example of that puzzle-based distillation process. But we are also working on a wide range of completely new neural network architectures that are more effective. So think about it. Transformer is a dreadful choice for neural network design. Its computational complexity grows quadratically. meaning that it's very expensive to run and almost prohibitively expensive to execute, especially with longer sequences. And I think it's obvious that we can get rid of it with time. Yes, so people tried with other architectures. Mamba is a perfect example of a non-transformer architecture, saying that it's not as simple as that. It's not as easy to displace what is now quite a few years of research with a new novel idea. So what we have been experimenting with are hybrid neural network architectures. So neural networks that are mostly composed of Mamba-like or non-transformer layers, with only a small proportion of transformer neural networks. So most of the neural networks that we are releasing right now fall into that category of hybrid neural networks, where only a small proportion are transformer layers. And of course, there is an ongoing work on mixture of expert architectures that are again helping with inference cost. There is a lot of efforts that are independent on each other, and you can need to use all of them if you want to squeeze out the maximum performance from your deployment. So this inference space is getting admittedly quite complicated.
So are we reaching a point where all those efforts and software optimizations matter more than hardware scaling?
Well, no, because you still have to execute it on something, yes? And a lot of those tricks are designed around the capability of the hardware, yes? So you cannot just simulate NVFP4 in software, like in a sense, the initial transformer engine scaling was done in software because it was done across entire matrices. Now, when you're trying to scale at those like 16 number chunks of the matrix, you really need to execute that in hardware. Otherwise, all of the benefits of the quote-unquote trick will disappear because of the overheads. Yes, similarly, it's great to talk about very large-scale mixture of expert deployments, but a lot of benefits would disappear if you don't have enough networking to allow you for GPU to GPU communication. So all of those things need to come together. Hence, this continuous theme in everything that Jensen says around end-to-end platform development. Like those optimizations have to be implemented end-to-end, from the GPU design through server design to networking, data center storage design, and then throughout the software stack.
I have a background in virtual desktop infrastructure, so a lot of we use a lot of GPUs in providing a great user experience, and there was always kind of a balance between latency versus quality or accuracy when it comes to, for instance, quantization. The more you quantize or the more you compress, well, obviously the latency is potentially lower, but the accuracy and the quality is impacted as well. So how do you balance latency versus accuracy in real world deployments?
Sure. So it's unavoidable. Yes. Dimitri, who is the main person in my team that deals with inference, he has spent in 2022, I think, 2023, a lot of time trying to figure out how to represent that relationship and how to talk about it. And right now, I think the way that he invented it became a standard of communication of the trade-offs between latency and throughput. In effect, there is just a curve, yes, and that curve is unavoidable. Like the lower latency you have, you will have lower throughput. You can move that curve up or down, i.e., moving that entire Pareto frontier, making all of the models more cost-effective within a certain latency budget, but that latency curve is not going anywhere. Yes, so everyone that has an application, they need to ask themselves a very simple question: what is the maximum latency my application can accept? And just target that. Yes, because trying to overdo it, trying to target for too low latencies when there is no need, it will cost you. Yes, Similarly with accuracy. By the way, as those neural networks are becoming bigger and bigger, many of those interventions do not lead to immediate degradation in model performance. So very frequently you can quite aggressively distill and quantize the model without any noticeable change in neural network behavior. But there is a point when, if you go beyond that point, you will notice degradation in neural networks performance. And then you have to ask yourself a question of, well, do my unit tests still pass? Yes. And if you have a well-organized team, if they have a good evaluation pipeline, and if they can quickly answer those questions, they will be able to do great things by making some of those compromises. If you don't, then it becomes close to an impossible task. But yes.
And I think this is just another great example why the development the development when it comes to models, but both the software stack and the hardware stack really matter, because the fact that you can now scale out GPUs just across a single node, NVLink and NVSwitch are technologies that existed for a while, but Nickel now enables you to scale with the with the undergoing growth of those models. And the fact that they just simply demand more, while your business is still, expecting a certain SLA as well.
And the graphs that Jensen was showing during quite a lot of our recent events, they also demonstrate that you can get significantly more cost efficiency, especially with larger scale deployments. So there are some tricks that you can use when you have a certain critical mass of GPUs that you cannot use without them. So sometimes it's counterintuitively cheaper, not counterintuitively, it's cheaper to run at larger scales because there are certain things that you can do.
We love tricks. Now, with all of your experience, especially at the customer side of things as well, I love to dive into the kind of the topic of people and process. Because there's also a ton of misconceptions around around inference. And what are some of the common misconceptions that teams might have about it?
So I'm not sure about misconceptions. I think all of that is relatively new. So the total number of people that knew how to operate large scale, very large model inference systems just 2 years ago was much closer to zero than not. Yes. And I think we are all learning, like the entire community. Everything that I've just discussed, it's not rocket science. And neural networks are actually, from software development perspective, relatively simple programs. Yes, so I think the community is learning extremely quickly, and we are getting more and more very competent people that not only understand theory sufficiently, but have some level of practical experience, at least managing medium-scale deployments of those models. The challenging bit here is that despite this tremendous growth in the number of those people, that number is still small. Still, you get very broad range of skills. It's not like universities have degrees that focus on large language model inference, and maybe some do, but they are far in between. And also those neural networks are changing. Yes, so we've discussed very briefly today all of the KV caching mechanisms, disaggregated execution mechanisms. But we now see, for example, non-autoregressive neural network architectures that are fairly reasonable that might put all of those optimizations into the bin. So I think it's not about necessarily misconceptions. It's we still don't have enough people that are great in this space, and we still have much more to learn. So whomever those people are, they have still a lot to learn.
When you take your own learnings from customers or feedback from customers, when it comes to inference, how do you collaborate with NVIDIA's engineering teams or product teams to bring that feedback from the field?
So NVIDIA is an exceptionally shallow organization, yes. So it's actually very easy in NVIDIA to just pick up a phone and call someone. And people are more frequently than not very reasonable. So if you articulate why something is important, it will get prioritized more frequently than not. So I don't think at NVIDIA we necessarily have that problem. Of course, the field is progressing at an incredible rate. And of course, we are bombarded by requests left, right, and center. But we are somehow okay at dealing with that. I'm not sure whether there is a secret sauce to it beyond the fact that Jensen enforces certain culture in the company. But it works for us, and I'm hoping that it will continue to work for us as we grow, as we bring on more people.
So you mentioned early in the beginning of the conversation, you mentioned some tricks. You just mentioned some secret sauce. So are there any kind of memorable customer stories or lessons learned or some of the secret sauce that you could share around optimizing inference where it might have unlocked something completely unexpected?
Well, so there is a lot of theory around some of those inference techniques. A lot of theory that has very limited grounding in experimentation and in data gathering. Very frequently we were surprised by our own misconceptions about the technology ahead of us. So I remember talking theoretically about disaggregated execution a very long time ago and discussing it with the team like an interesting idea, but an idea that is impossible because the sizes of those KV matrices are too big to be practically transported. But I think very first experiments with very first customers showed us that was not the case. That the modern networks can in fact move those segments fast enough. There's very similar story around storage of those KV components. There are a lot of misconceptions around, can we store them into the file system? Can we store them and retrieve them fast enough? I think the first engagements with customers, they just, what they bring is this grounding in experimentation, grounding in data collection that actually reveals the truth. And very frequently the truth is much simpler than people think. So that is why it's important that we work with some of those key customers because through them we learn. This helps us prioritize, and we make life easier for the rest of the community.
Awesome. Well, thanks for answering a ton of questions, which I had around the topic of inference. Now let's dive into experiment number 3, the lab report. Basically kind of a shared set of key takeaways that we take from this episode. Number one question I have. So if there's kind of to you one key takeaway, one thing that listeners should remember about, making inference efficient, what would it be?
Sure. Really not overthinking the process. So optimization, computational efficiency, it's really an incremental process. Yes, you deploy something that is reasonable. Yes, you measure its performance. You look at where the biggest bottlenecks in its execution are, and you focus on that problem and that problem alone. You measure again. You look at where the biggest bottleneck is. You try to understand its root cause, and you focus on that and only that. It really doesn't have to be particularly difficult, and many people are facing same problems as you are, so a lot of the solutions exist, be it sometimes in a very immature format, but I think that's the process. It really doesn't have to be particularly difficult. It starts with deployment of a good enough pipeline and its ongoing profiling and optimization.
Yeah, I think definitely a great takeaway. Another one for me personally is the impact of both the hardware as well as the software stack, and that you definitely should not just focus on choosing the right GPU, or and like you mentioned that earlier before, the ecosystem of software components is so big and so rich that there is a solution for basically anything, and there's no kind of one-stop thing or one-stop shop when it comes to no, I won't say one-stop shop, but there's no kind of single golden solution to rule them all, right? So there's no kind of ring from Lord of the Rings.
No, not quite yet. At some point we might get there, but right now the models are still changing very aggressively. So not today, no.
Well, and that's a great segue into my second question. So, what's your prediction for how inference will evolve in the next 12 months? Like hardware, software, both?
So, I think it's becoming obvious that mixture of expert models, one, work, and two, that they are a good idea. Yes. So, I think we will continue to see their growth in a sense that we'll continue to see much bigger, but also possibly much more sparse neural network architectures. That's one dimension that I'm quite confident that we'll see a lot of progress. That will bring a lot of challenges to the inference process, because inference of mixture of experts, I think it's still our thinking about it is still very primitive. I think we can do still much more when it comes to optimization of its execution. So, we've already started to see automatic auto-scaling of experts. So neural networks that might have, more instances of one expert versus another. But I think we'll start to see more interesting automatic kind of load balancing and auto batching per expert. That will make it a bit more complicated, but hopefully bring much more computational efficiency to the problem. I think a hybrid neural network or non-transformer neural network architectures are here to stay, and I'm hoping that we will see much more progress around non-autoregressive neural network development, because that autoregressive loop is not necessarily beneficial for anyone. So if we can get rid of all of it or part of it, that would be great. And there is some great work focused on diffusion language models that might or might not be displacing the transformer autoregressive family of models going forward, and that would change the inference landscape quite dramatically. We're of course seeing right now a very significant impact of multimodal architectures. Yes, so vision language models, but also models including wide range of other modalities, and those bring a lot of new challenges to the inference story, because on top of all of the complexity that you already have, you have potentially the vision embedding models that you need to do, especially when it comes to video, real time decode, and possibly if you're generating footage encode. So I think we're going to continue to see this incremental increase of complexity of inference as we go along. In a sense, it's unavoidable. Like, think about it. Within a chemical lab, like, you could distill some alcohol within a flask with a burner, but that approach cannot bring you to distilling millions and millions liters of alcohol or other chemical every week. You completely need to change the way you operate. You suddenly need entire refineries. And that's where we're heading. And it's not a coincidence that Jensen is referring to AI factories. It's a, I think, very good analogy for what we're observing, like transition from the lab, where a single scientist was kind of pouring liquid from one flask to another, to entire building size boilers and distilling facilities.
This is why I really love the DGX storyline. With the Spark being announced and released earlier in 25, you kind of you enable basically everyone to build something based on the entire DGX family and the software solutions you can run on top of that, like DGX Lepton. it's so easy, quote unquote, to lift and shift the thing that you build in your lab and take it to production, to a bigger DGX system, or even to a factory. And I think this is definitely something that you guys have really listened to your user community. Like the developer experience on the thing on the entire DGX platform is beyond something I've seen before. So yeah, definitely big compliments.
And also an entire family of like businesses that are trying to target smaller groups of developers or of engineers that can provide like not a data center, but like a solution that can be handed over to someone, placed on a desk, connected to a network, and serve a group of 5 or 6 people in the office. I think we'll see a lot of amazing things out of that system.
Awesome. Well, I have one final small question before I let you go. If you could run any model ever built instantly, what would you use it for?
So one of the things that I'm personally very excited about is this emergence of reasoning models, but not just like reasoning models that we've gotten used to in the last couple of months that that generate a bunch of reasoning tokens and provide a slightly better solution. But I think we're up to something, especially when it comes to very complicated problems that are verifiable. I think we are and we will be making very significant impact on the way research is conducted. Yes. So today we've discussed a lot the problem of inference of neural networks, but I think we're starting to see something slightly different, like emergence of thinking machines. So machines that, when given a problem, they will not just execute some like random agentic pipeline for a couple of minutes, an hour, but will be able to spend a lot of computational cycles, months, on a single problem, conducting very broad literature reviews and possibly conducting experimentation. So, delegating execution of HPC codes in physics, chemistry to the same HPC systems on which they live by themselves. I think we'll see a very interesting shift in capabilities in overall research, very similar to kind of what the emergence of internet did for dissemination of academic literature. And I'm genuinely looking forward to how this space of technologies will evolve. And the way this ties back to your question is, the better job we do at optimizing the models, the lower the cost of a single token becomes, the more ambitious work other people can do. So in a sense, like every time we optimize a model, we enable someone else to do their work, and that's very rewarding from my perspective.
Awesome. Definitely an awesome quote to end the conversation with. So if people want to follow you, where can they follow you? Somewhere on the socials? Or
I predominantly publish updates from what my team and broader NVIDIA is doing on LinkedIn, and you cannot miss me with my surname. So.
Awesome. Well, Adam, thanks so much for being a guest, and have a great day.
Thank you.
Thanks for tuning in to the Private AI Lab. Don't forget to subscribe on Spotify, Apple Podcasts, or YouTube, and visit Johan.ml for more insights and experiments. Experiment complete. Until the next one, stay curious. Private AI Lab.